And honestly,
Okay. Good morning, everyone. I want to welcome you to another statistical machine learning class. Of course, today we're going to finish our theory of convex function that we started on Monday. Of course, before now, I've walked you through how to investigate convexity. Why do I need to investigate convexity? Or maybe I'm actually seeking for minimum value of a function. I want to minimize a function. And of course, before we can be guaranteed a global minimum, if we don't want your algorithm to get stuck in a local minimum, then it becomes necessary to investigate the convexity of your function. I remember before now, I've walked you through the meaning of what makes a set to be a convex set. And I've also walked you through different kind of differentiable classes to, if you actually want to investigate convexity, of course, I walk you through the first differentiable class, the first in the differentiable class that we call C0, where your function is continuous but not necessarily differentiable. Okay, I also walk you through the second in the differentiable class that we call C1, where we actually where the function is continuous and the derivative exists to order one. I think I walk you through that as well, how you can use that to investigate convexity. And I think we stop at the third in the differentiable class. The third in the differentiable class where your function is continuous and it is differentiable up to order 2. Okay, how do we actually use that to investigate whether a function is convex or not? And if a function is convex, we can also use that to investigate the type of convexity. We want to see whether it is strongly convex, or it is strictly convex, or it's just convex. Okay, so I remember I stopped here on Wednesday. But you know what? Where I want to start from today, I'm actually going to differentiate between different type of convexity using different classes in the differentiable, using the different differentiable classes. And I need you to pay attention. Of course, how do we actually, for instance, if you have a function, let's pay attention. If you have a function that is this, C0, you know what I mean? You have a continuous function, but not necessarily differentiable. You want to investigate whether it is strictly convex or strongly convex. Okay, let me tell you this. If this guy is already convex, based on what we've done before, based on triangular inequality, based on the fact that when you choose 2 points, in the domain of the function and you connect a chord and you realize that to stay inside the function, of course, that is how we investigate that it's convex. But do you know that if I want to make something, a function that is convex, to be, strongly convex, I'm going to say that again. If I have a function that is continuous, not necessarily differentiable, it is convex, but we want to make it strongly convex. Do you know why I need strongly? Let me quickly explain that. Strongly convex implies strictly convex, and this implies convex. Okay? Now, even though we want convex, if it is strictly convex, the strictly convex is actually saying that we actually going to have curve direction, even though we can still have maybe a flat. Okay, but when you're taking a look at strongly convex, okay, we're actually going to have curve everywhere. Okay, now how can we make a function that is a convex to be straight, strongly convex? We can actually, which means what we're actually trying to do is to see how we can, excuse me, how we can reduce the function. Now reducing, don't forget what we're looking for initially is to minimize the function. Now we can reduce the function by another convex. Take a look at this guy. That's another convex. I walked you through this the other time. A norm is convex. Square of a norm is convex. And non-negative scaling, of course, is also non-negative scaling is going to have mu over 2, provided mu is positive. Okay, you remember non-negative scaling preserve convexity as well. So this will give us a strongly convex. Okay, I'm going to say that again. If f of w is convex, and I want to make it strongly convex, okay, what I'm actually going to do, I can subtract this guy. But I have to make sure what I'm subtracting also have to be convex. Okay, so when I do that, I can achieve a strong convexity for a continuous function that is not necessarily differentiable. And I'm going to give you, if you take a look at this, do you know that in linear regression, where we're trying to minimize, okay, a loss function, you feed it a model, a straight line model to data, and you want to have a measure of how your model fits your data, we normally go by way of a least square. Has anyone has heard about least square before? Okay, now let's say f of w represents that, but if you have so many variables, maybe you're working on multiple linear regression. I remember what I did when I was doing my capstone project in Nigeria. At this level, I work on the effect of exchange rates or inflation rates and consumer price index on the gross domestic product of Nigeria. So, I got three variables, so three explanatory variables. What if in a situation where I got a lot of explanatory variables? When I have a lot of explanatory variables, okay, one of the assumptions using multiple linear regression is that there shouldn't be multicollinearity. Has anybody heard about multicollinearity? Okay, multicollinearity. Okay, multicollinearity. Multicollinearity is a problem in regression analysis where so many independent variables are correlating. When they are correlating, okay, we're actually going to have a problem of noise. It's going to be noisy, and your module will overfit. Okay, your module will overfit. Okay, your module will overfit because there's high variance. Okay, because there's high variance, because there's too much. We have so many variables. Your module is going to suffer for what I call over parameterization, and because of that, okay, we normally introduce a regularization. Take a look at that guy. That's a regularization. Okay, in ridge regression, in lasso regression, we bring in a regularization so that we control the over parameterization. Okay, but when you bring this in, you got to make sure what you're bringing in is converse. If f of w is already converse, okay, of course, this guy, okay, well, no square of norm is converse, and lambda over 2, provided lambda is positive, we have I've also shown you in this class that non-negative scaling also preserve convexity. Okay, so if that happen, okay, now the implication here, why do I need a strong convexity? The implication is that my algorithm will not get stuck because there is curve everywhere. If there's a flat, if it is flat, it can get stuck. Okay, but when something is a curve, it's just going to be moving, okay, until it attains the global minimum. Okay, and let me tell you this, that will make your algorithm to converge faster when your convexity is actually strong. Okay, and you're actually going to have a stable result. Okay, that is the implication here. Okay, I want to go back to the first differentiable class. In the first differentiable class, where we have C0, don't forget that. Okay, you are actually trying to minimize a function, and the function you are minimizing is not necessarily differentiable, but it's continuous. Can we have a way to use the first differentiable class to differentiate between converse, strictly converse, and strongly converse? I'm going to say that again. You have a function that is continuous, but not necessarily differentiable. Okay, how do you investigate the types of convexity with that? I need you to pay attention. Okay, whenever I have this guy, I've told you from day one, that triangular inequality is actually saying when you choose any 2 point, okay, maybe between, when you draw a line between them, okay, that stay inside. That's what it means that our function is going to be less or equal to that. It means to stay inside. Okay, that is how we can use the first differentiable class to investigate convexity, just converse. But how do I use the first differentiable class, C0, to investigate strictly converse? Please pay attention. I'm dishing out most important information now. The moment you get stuck, you don't understand, please ask me a question. I just show you now, just giving you a formula. That's a formula if I provide, if I want to use the first differentiable class, which I call C0, you have a function that is continuous, but not necessarily differentiable. How do you use that to investigate convexity? If you want to do that, okay, the moment you're able to show that the function stay inside, okay? Now, but how do I show for straight? Please pay attention. To show for straight, I don't need equality. Do you know here? Look at this, the difference here and here. The first one say less or equal, which means there's possibility, it's on the line, okay? But the strictly is going to say it shouldn't be on that line, it should be below the line. Does that make sense? That's what we're trying to talk about here. But how can we make it strong? Okay, because I said something the other time. Strongly converse implies strictly converse, and this implies that, but it's not the other way around. You can have a function that is convex, may not necessarily be straight. Does that make sense? Just wanted to know that. Now, it means I need extra information if I want to make it strong. Then, because if I want to make it strong the other time, what do you think I did here? Making it strong, I'm actually subtracting something to make it strong. Okay? I'm subtracting something to make it strong. Now, take a look at here now. Okay? Oh my God. Can you see that? I'm actually subtracting that from this guy. Okay? I'm subtracting. I want to make it strong. I want a situation where my algorithm is not going to get stuck, okay, in a local minimum. I want a situation where my algorithm is actually going to converge faster. Okay? Now, you can see what I'm subtracting. Minus, of course, theta. The theta is, the weight, which is going to go from 0 to 1. And, of course, the U and V is, those are the 2 points that you choose in your domain. So, and the square of the difference of norm is actually preserving convexity, okay? And, of course, theta. The theta is positive because it's a probability value. Theta lies between 0 and 1. That's a positive number, okay? And mu, well, the mu is also positive. So, with this is the way I can actually, guarantee strong convexity when I'm using the force in the differentiable class. Is there any question? I need to take a look at the three one at a time. Here we are only using the force in the differentiable class. We're only using a continuous function that is not necessarily differentiable. What I've done right now, I've been able to show you the condition for convexity. I've been able to show you condition for strong or for straight convexity and for strong convexity using that differentiable class. You know what? I think I gave an example here. Take a look at this. Even though s raised to power 2 is convex, s raised to power 4 is also convex, but one is stronger than the other. And I wanted to see. Can you pay attention to this? You're actually going to see now here. 1 second. Let me use my pointer. Now, if you're going to see here, this is s raised to power 4 is more or less flat. Okay? It is flat. This is not strong because we don't want any flat direction when it comes to straight. I wanted to take. When it comes to strong, if you take a look at what I have here, okay, why if you want to look at the intensity or the degree of convexity, this is the strongest one. Do you know why this is the strongest one? Because this guarantee a curve everywhere there's no flat direction. Okay, let's take a look. Do you see any flats here? That's why a square is strongly convex. But in the case of s raised to power 4, okay, this could be straight, but this is not strong because we can see some flats. There's possibility, okay, the algorithm may kind of slow down. Even if it doesn't get stuck, it can get slowed down. Okay, and when we want a situation where we want our result on time, we don't want an algorithm that will continue to iterate a lot of iterations without converging, on time. Okay, I'm actually moving now. Once again, I'm defining the strong convexity and the straight one. The straight one, okay, what the difference? This have to be less than. Okay? The straight one. Okay? The ordinary convex, less or equal. The straight one, less than. The strong one, there's something need to be subtracted. Did you see that? For the strong one, something need to be subtracted. But what you're going to subtract, you got to make sure it's also convex. Okay? Now, I'm seeing some questions now here in the next assignment. Now I'm giving you, these are the convex functions. I can ask you to investigate them. Okay? I can ask you to investigate them for convexity. I can also ask you to investigate them for strict converse or for strong converse, if they are converse at all. What kind of converse are we talking about? And we also have concave functions. But right now, we're not interested in concave. We are interested in converse. Okay? But let me tell you this. If I change the sign back to greater than sign, then I'm talking about concave. Does that make sense? Okay. Now, these are other examples of converse affine functions. Okay? It's converse. Talk about the linear regression model. When you have a multiple linear regression, if you write that, when you are trying to seek minimization, you're trying to seek, you're trying to minimize the distance between the model and the observation. You want to have a measures of goodness of fit. You're minimizing, okay, and after minimizing that, you want to get an optimal values. The optimal values of the regression parameter, affine functions are actually converse, which means what you're going to be getting will be global minimum. All norms, any norm is converse. Any norm, okay? Any norm is actually converse. And the square norm is converse. The maximum of something is converse. Okay, all of this is converse. We've been able to investigate that. We've been able to verify that. Now, if I want to talk about an n by n dimensional space, okay, now the general affine function is also converse. Okay, the logarithm of the determinant of S is not converse. If you take a look at what I have here, okay, please pay attention. This guy, the logarithm of the determinant of S is concave. It's not converse. You can investigate that. Okay? So now I want to move right now. And I need you to pay attention. I think I've been able to walk you through the first differentiable class without any derivative, because in the first differentiable class, the function is continuous but not necessarily differentiable. I think I've walked you through how you can use that to investigate convexity and types of convexity. But you know what? If I'm talking about the second in the differentiable class, C1, what is the condition for convexity? The condition for convexity is that, we should have the function should be above the tangent line. Okay, take a look at that here. Can you see that? And this is the function. Do you see that curve? And this is the target line. You can see that function is above. I remember in your high school when you're talking about difference between areas, okay, where you actually use definite integral, where you're going to say when f of s is greater than g of s, you're going to do f of s minus g of s integral ds, where you need to identify which function is at the top and which function is at the bottom. Okay, so the first order condition is that the function should stay at the top. The function here is the curve. That is at the top. Take a look at that. And this guy here shows first derivative. Do you see that? That shows first derivative. And even if you have more than one variable, there's so many variables, okay? If you have so many variables, you're going to have this. Take a look at that. Can you see that? Where you're going to differentiate with respect to x1, respect to x2, you're going to have, that's going to be a gradient. You're actually having a multivariate gradient. Does that make sense? Take a look at that. Okay, the first order condition. This is the first order condition. Okay, you have a function that is continuous, and the derivative actually exists up to order 1. But you know what? I'm going to spend more time on the second one. This is what we normally use. The third differentiable class. You remember the third differentiable class C2. The condition, okay, has to be, please, I need you to pay attention. F is convex. Number 1, the function has to be continuous. Okay, the function must be differentiated twice. It must be differentiable twice. And when it is differentiable twice, if it is greater or equal to 0, okay, if that is greater or equal to 0, I'm actually going to say it's converse. Okay, but let me tell you this, greater or equal to 0, I'm actually going to say it's converse. If it is just greater than 0, I'm actually going to say it is strictly converse. Take a look at that here. Can you see that? Strictly converse. When it is greater than 0. But when it is greater or equal to 0, that is just converse. So right now, I'm actually talking about the second order condition. The second order condition applied to C2. What do I mean by C2? That is the third in the differentiable class, where the function you're seeking to minimize is actually, continuous. And of course, the derivative exists up to order 2. Okay. I need you to pay attention now. I want to walk you through an example. Okay. How we can use a second order condition to investigate convexity. I told you the other time, if I have this guy, take a look at this. This is my function that I'm actually seeking to minimize. Please pay attention. If you don't understand, ask me a question. I'm here, okay? Are you ready? Okay? You all ready? Those of you at the back, can you hear me? Okay, please ask question. If you don't understand, if you get stuck, ask question. Now, I want to walk you through an example now. Okay? Oh, what I'm having right now is a quadratic function. Take a look at that. If I want to use second order condition, which means I actually want to use C2, which is the third in the differentiable class. I'm going to differentiate first time with respect to x. Can you see what I got? And I will differentiate second time with respect to x. Of course, I'm actually going to get p. This is converse. Okay? It's actually converse. Okay? Provided, p is what? It's positive. Does that make sense? That's what I said. If p has to be non-negative, okay, that is going to be a converse. But situation where you have a negative, okay, if you have a negative, if p is a negative, that will be concave. That's not converse anymore. Okay? It's an example that I just show you now. Now I'm gonna show you an example in a least square that is common. This is a least square, right? That's a function that you actually want to minimize. Okay? AS is the model. Maybe B is the data. You actually want to see how the model actually fits the data. That's what we call goodness, the goodness of fit. Okay, you are interested in how the model actually fits the data. Now, you're now trying to, because the model, you don't expect the model to perfectly fit the data because we live in a stochastic environment. Model does not give exact characterization of reality. You now want to measure the gap. You want to minimize the gap. That's why you are subtracting. You want to minimize the gap. And for you to do that, if you want to use the order condition, please pay attention. Okay, when I do the first derivative, that's what I'm going to get. When I do the second derivative, that is exactly what I'm going to get. When I have a second derivative now, okay, with that, because I'm doing A transpose A, the A transpose A will lead to sum of squared. Because it's like you're having all the A here, multiplying all the A here. So it's going to be A1 squared plus A2 squared, and so on like that. That's going to be converse. And that's what we mean. Now, I've just given you an example on a univariate when I'm not focusing on one variable at a time. But what if in a situation where in my objective function, what I want to minimize as more than one variable? Please pay attention. If it has more than one variable like this, you can see that's a bivariate. F of xy. You've come across that in theory of statistics. Okay? In a 5101 class or 4101 class, where we are actually talking about a probabilistic representation of two variables at a time. Now I have f of xy, and I actually want to, I want to investigate that for convexity using the second order condition. If I'm going to do that, I'm actually going to apply this. Can you see that? This one is a general one where I have from x1 up to xn. If I have a multivariate, okay, if I have so many variables, but this time around now, I'm actually having two variables, okay? I'm having two variables, okay? What I'm going to do, I will differentiate with respect to x. I will also differentiate with respect to y. Then I will do that again, okay? Do that again. That's exactly what you have here now. And provided that is greater or equal to 0, you can ascertain convexity. Okay, how do we investigate that I find is convex? Please pay attention. You are given this. Okay? And, you know, if you take a look at this, right? That is the formula in the convexity. Okay? Now, instead of you to have A transpose S plus B, okay, there's something I needed to see. Here, instead of X, what are you going to plug in? You plug in the whole of this. You plug in that into this equation. Pay attention. It's getting tough. I need you to pay attention. Okay? Look at the board. Look at what if you don't understand, ask me question. Pay attention. I'm plugging in this guy inside here. Then I have this. Easy. What did I plug in? I plug in. Where is that guy coming from? Where is this guy? This is from the model. This one. It's from the model of convexity. Plugging into X. I have this. Then I simplify. When I simplify, I got this. Okay? This is the chord. This is trying to say is stay on the line. Equality. Stay on the line. Okay? This is convex. But because it's equality, it is not strictly convex. It is just convex. Please pay attention. An affine function is convex. Now, I just want to show you the examples of multivariate convex function. This is an affine, this is quadratic, and this is one norm. Okay? Just trying to show you the picture, the image. Okay, I'm moving. Now, I'm seeing a lot of assignment questions, test questions, exam questions, and that is why we are at a critical time now, period, now, and I need you to ask me question if an area is not clear. Are you ready? Okay, take a look at this. You want to investigate this guy for convexity. They say, which of the following are convex? You have an absolute value S, you have a cosine S, and you have S squared. You want to investigate each of that for convexity. And you know that if you want to go by way of for the first differentiable class, if you want to use the first differentiable class in investigating that, this is actually what is going to guide us. Okay, now I needed to pay attention to this. I want to apply that to absolute value S. Take a look at what I have now. Okay, for absolute value S, you see what is going to replace? I can rewrite that as that. Okay, can you see that? I can rewrite that as that. Now, if I have, if my function, if f of s, okay, if f of s equal absolute value x, and I want to use, it means I'm just going to plug in this guy, right? So instead of me to have just x, if you put this one inside here, please pay attention. If you plug in that guy, I'm having this. Is there anyone who's not clear about how I got that? I plug in what you have inside here. Can you see that? So I'm plugging in, then I got this. When I get this, I'm actually going to use the law of triangular inequality. The law of triangular inequality. Okay, now when I have something, when I have this guy, okay, according to triangular inequality, that guy absolute value of something plus something will be less or equal to this. Take a look at that. Where I'm bringing the lambda out and 1 minus the lambda out, because the lambda and 1, lambda is a probability, it's a weight. It's not necessarily, it doesn't need absolute value. You know why? Because it's already positive. The probability is positive. And the other one is going to, so with this now, I'm actually going to say, all absolute value, when you have absolute value function, is converse. Okay, now you can investigate the same for s squared. What if in a situation where your f of s is s squared? Okay, this actually show that. Okay, that's actually show that. Now, if you take a look at what I have here, this is just to show you that this is not the minimum, but this is the minimum that we want. Okay, that we actually call the global minimum. Okay, let me see. Okay, if I multiply this guy by negative, if I multiply by -1, the sign is actually going to change. If I have a less or equal, I multiply both sides by negative, it's going to change to greater, right? You know what I mean? So I can go from convex to concave. Does that make sense? That's what I'm just talking about here. Okay. Now, yeah, I think we have already mentioned that. Okay. I want you to pay attention now. If I want to use second order condition to investigate convexity, we can make use of eigenvalues. Let me quickly give you this information. We can make use of eigenvalues. We can make use of quadratic form. What is the meaning of eigenvalues? The eigenvalues will show us the direction of the axis. Okay? And how am I going to get my eigenvalues? I need to first set up my Hessian matrix. What is the Hessian matrix? When I have the second derivative. Okay? As the second derivative, maybe if I have two variables, for instance, if I have, this I need you to pay attention. I need you to pay attention now. Okay? If I have an Hessian matrix, what do we mean by Hessian matrix? Okay, if I have f of xy, my Hessian matrix is actually going to be this square, the s squared here, the y squared here, okay, and here the f, that square of the x delta y here that I have in this. Has anybody seen this before? Now, from the function given, I need you to pay attention now. If you want to use a second order condition, you need to generate your Hessian matrix. After generating your Hessian matrix, I'm going to say something right now. After generating your Hessian matrix, okay, after generating the Hessian matrix, you find the eigenvalues. Okay, the eigenvalues will actually tell us the spread in the direction of the spread. Okay, now if you get the eigenvalue, of course I'm going to get two eigenvalues from this. Okay, if the eigenvalues, please pay attention. If your eigenvalues, let's say the first one is 0 and the second one is positive. Okay, that is what we call positive semi-definite. You remember the positive semi-definite, we expect that to be greater or equal to 0, which means one of that is 0. Okay, well, if that actually happens, then that is convex. Does that make sense? That is convex. But situation where we have positive, there's no zero. If there is no zero, that is positive definite. Positive definite implies strictly converse. Does that make sense? I'm going to say that again. If you want to investigate convexity, you need a positive semi-definite. The positive semi-definite is going to tell you that after getting the eigenvalue for the Hessian matrix, one of them is zero, one of them is positive. That is a positive semi-definite. That indicates that it is converse. But if I want to know whether it is strictly converse, the eigenvalues, all the eigenvalues have to be greater than zero. But what if in a situation where all of them are negative, that we call negative semi-definite, that is concave? What if in a situation where one is negative, the other one is positive? You have the combination of a negative and positive eigenvalues. That is indefinite. Indefinite actually means it is neither concave nor convex. Do you get the information? Now I'm going to move. Now we have an example now. How can we show that this guy is convex? Okay, that's a natural log. When I differentiate it first time, this is what I got. When I differentiate it second time, this is what I got. And of course, 1 over s squared, that's a positive, which is greater than 0. Of course, that shows that negative log of s is convex. What about log of s? If I multiply by negative 1, is this still going to be convex? No, it's going to be concave. Okay. I'm actually moving now. I'm moving. Okay. I'm moving now. Okay. This is another example for convexity. I'm actually going to move because of my time. You can read through that. Okay. Now, I want to do this before I actually now want to demonstrate to you an example on how algorithm work. Okay? You have a function. You want to minimize this guy. And you actually want to test alpha, because when you take a look at this is how you can update xt plus 1 equal st minus alpha. Okay, delta f. Now the alpha, we want to know the size of alpha that's actually going to do the job. Now, when you try using alpha equal to 0.5, what happened? Okay, now I realize when I use alpha equal to 0.5, the algorithm reaches the minimum at step 1. We want situation whereby we don't want to spend a lot of time. We don't want the algorithm to iterate forever. We want the one that converts very fast, and that depends on how you choose the values of alpha. And we said for alpha equal to 0.1, the algorithm eventually converges, but takes more steps than when it is equal to 0.5. And when we choose alpha to be 10, instead of the algorithm converging, it diverges. We don't want that. Now, I'm going to show you how this is it. Please pay attention. Okay? Pay attention. Now, if you take a look at this, okay? If you look at what I have here, initially, you can start with 6. The x naught to be equal to 6. You need to start with the initial value, being a constant here. Okay? We start with the initial value of 6, and you're starting with an alpha equal to 0.1. Okay? We want to see how that is going to behave. Okay? This is the model. You're starting with x1 equal to 6. So the next one now, if you want to get x2, it's going to be 6 minus the alpha and the values of the derivative. Okay, this is a model, right? Differentiator, what do you have? That would be 2x minus 4, right? Plug in the first value. What is 2 times 6? 12. What is 12 minus 4? 8. That's why you have this guy here. Okay. Now this is a new value. Now you start all over. Okay, where your new value now, you're starting with 5. Now it's going to be 5.2. You continue, don't forget you come in here to put 5.2 in the derivative here. Okay, at the end of the day, okay, we realize that when you now have the same value, when you see that, then it means the algorithm actually eventually converge. Okay, I said at that step it reaches minimum. Okay, now you can try a different alpha, 0.5. Okay, when we try 0.5, 0.1 took a long time. We didn't show it. So it's going to go forever before it eventually converge. When I choose alpha to be 0.1, when I choose 0.5, okay, just one step, it converges. Because when I go for the other step, it's going to be the same value. Okay? And when you choose a bigger one, when you choose a bigger value, it doesn't, when you choose 10, alpha equal to 10, it doesn't converge. So which means the size matters. Okay? Now, that is for univariate. What if I'm dealing with a bivariate? Then I have this. Okay? And I'm having this as the starting point. Because I got two variables, I'm going to have one starting point for S, the other starting point for Y. If I got three variables, I'm actually going to have three different values at the starting point. This guy here, when I differentiate, do you know that here, this guy, okay, I'm differentiating this guy, okay, with respect to X. That's going to be the F dx right here. Okay, and Y this guy is when I differentiate in that with respect to Y. Please pay attention. Okay, with respect to Y. Okay, then I'm going to start. But here, my size is 0.1. Then I will start plugging in. Okay, that is the way it works. Okay, before I go. Okay, I think I put some notes here that you can read. What is the essence of convexity? Everything that we've been doing. Okay, why do we need that? But I wanted to spend more time on this. Oh my God, because I'm actually seeing assignment, exam questions. Take a look at this guy. For each of the following below, determine whether it is convex, strictly convex, or strongly convex, or none of the above. Do you know what I want you to use? I want you to use the second order condition, where you're going to set up your Asian matrix, and you now find the eigenvalues. When you find the eigenvalues, when the eigenvalue includes 0 and positive number, that is convex. When we call that positive semi-definite. But it's actually going to be strictly convex if, the diagonal, the eigenvalues, they are all positive. They are all greater than 0. Okay, if you have a mix between a negative and a positive value, that is indefinite, and indefinite does not qualify to be a convex or concave. Okay, so you can investigate all of that. That's all I got for you today. Is there any question before I go? Make sure you all stay safe and have a lovely weekend. See you on Monday in person. But for now, everyone, let me see it. This. Someone is looking like this week's homework are due on Sunday. Is matrix operation going to be? Yeah, the next. The for the person that asked the question online, the next assignment will be based on what we did this week. So it's going to be based on convexity. I don't know if I've answered your question. It's going to be based on convexity. Okay, thank you too. But for now, it's the same. Okay, go ahead. You say you have a question. Go ahead with your question. The person online, go ahead with your question. I don't know if you are talking. I'm not hearing you. Oh, is there still going to be a Zoom on Monday? No, no Zoom on Monday. In person. We're meeting in person on Monday.